This is the last lesson in the core section of Logic, Language and Information 1. We've learned about the language of propositional logic. We've learned about meaning or semantics for propositional logic, interpreting formulas in truth tables and using these interpretations to analyze formulas and relationships between them. And we've learned about one kind of proof for propositional logic, proof trees. In this lesson, I'll explain how it is that truth tables and trees agree in their verdicts. This is moving from learning how to use tools to analyze logical relationships to understanding how these tools work. Here's an analogy. Maybe you remember some elementary geometry and the idea of an equilateral triangle. This is a triangle in which all of the sides have the same length. So I've got a three-sided triangle in which every side has the same length. Now, there's also the idea of an equiangular triangle. And this is a triangle in which all of the angles have the same size. So the first one here is equilateral, and the second one here is equiangular. These are two different ways of sorting out triangles. One by comparing sides, and the other by comparing angles. Now, it's not too difficult to show that if a triangle is equilateral, it's also equiangular. So I've got an equilateral triangle, the interior angles are the same. It's also not too difficult to show that if a triangle is equiangular, then it is also equilateral. This means that the two different concepts, equilateral and equiangular, cut in the same place. The equilateral triangles are the equiangular triangles, and vice versa. Now, the same goes for logic. The truth table valid arguments are the truth tree valid arguments. The satisfiable formulas, those that can be made true together by way of truth tables, are the consistent formulas, those which have trees that stay open. The soundness result is one half of this equation. If a set sigma of formulas is satisfiable, then a tree for sigma stays open. So, suppose we have an interpretation which makes all of the formulas in sigma true. So I have an interpretation which makes all of these formulas have the truth value true. Then if I process sigma with the tree rules, I'm getting a tree which has got branches with formulas in it, like this. Then at least one branch of this tree stays open. Now, why is this the case? We're going to show this using the interpretation that we have over here. All of the formulas that are in sigma are true in the interpretation. So we know that none of the formulas here can close. This set doesn't contain a formula and its negation, since a formula and its negation are not both true according to this interpretation I. The interpretation, if you like, provides a safe zone where none of the formulas in here clash with each other. Our job will be to show that as you follow the rules of the tree, at least one of the branches that we get stays in this safe zone. And so eventually, we'll find that one branch of the tree, as it's extended, one branch of the tree stays safe, and as a result, stays open. And the result is that if the set sigma is satisfiable, if there's an interpretation which makes it all true, then it is consistent. Swapping this around, this also tells us that if sigma is inconsistent, if a tree for sigma closes, then it is unsatisfiable. There is no row of a truth table that makes sigma true. So to prove this, we need to show that each of the rules keep us in the safe zone. So let's check the rules. We check these rules one by one. If A and B is true in some interpretation, then it follows that A and B are both true in that interpretation, because a conjunction is true only if both of the conjuncts are true. So if the premise here, A and B, is safe, so are the two conclusions. On the other hand, if A and B's negation is true, then A and B is false. So one of A and B have to be false. So either it's not A, which is in the safe zone, or it's not B that's in the safe zone. And we don't know which one necessarily that is, but we do know that one of them is going to be safe. It depends which way we made A and B false. Do the same thing for the other rules. If a disjunction A or B is true in my interpretation, then maybe it's A that's true, maybe it's B that's true, but one of them is going to be true. Similarly, if the negation not A or B is true, then indeed A or B has to be false, which means that both A and B are false, so both its negations, not A and not B, are false. If a conditional A implies B is true, that means that either A is false or B is true, so either the not A branch will be safe or the B branch will be safe. On the other hand, if A implies B is false, if its negation is true, then A has to be true and B has to be false. Finally, for the binary connectives, if and only if B is true, then A and B have the same truth value, which means either that A and B are both true, or A and B are both false. Or if and only if B is false, if its negation is true, then either A is true and B is false, or A is false and B is true, because they're the only two ways they could differ in truth value. The last rule was the double negation rule, which says that if not A is true, then indeed A has to be true as well, because if not A is true, then not A is false, and that means that A is true. So we've shown that each of the rules keep us within the safe zone, and this completes our justification of the soundness result. If sigma is a set of satisfiable formulas, then it's consistent, or if sigma is inconsistent, then it's unsatisfiable. Completeness is the converse of this result. This tells us that if sigma is consistent, if a tree for sigma stays open, so I follow my rules, do my tree, and if one of these branches is open, then there is some interpretation that makes sigma true. For this, we start with a completed tree for sigma. So we've got our tree, and I've got an open branch. The aim is to show that this open branch provides the information that we need for a model. And for this, we don't start at the top of the branch and work downwards. We start at the bottom. But here it's not the last formula in the branch, it's its logical bottom. It's not the simplest, it's not the last formula we end up with, but the simplest statements in this branch, which are the atoms and the negated atoms, those formulas which are the logical endpoint. These provide an interpretation. So if I have P in my branch, then my interpretation is going to make P true, and if I have not Q in my branch, then my interpretation is going to make Q false. And if my language contains the formula R, but neither R nor not R is in the branch, then I'll interpret R with 0 or 1, whichever I choose. Now, because this branch is open, there is no clash in the interpretation of atoms. I'm never given inconsistent guidance, which says give this value 1 and give this value 0. So we've got an interpretation. The aim then is to show that everything else in the branch is also true. Now, everything else in this branch is a complex formula, and since the tree is complete, that formula has been processed. So what we do is we claw our way back up from simpler to complex formulas, from the output of our rules to their inputs, and we show that if the outputs of a rule are true in an interpretation, so is the input. So everything in this branch is true. So let's check the rules again. To check that these rules work, we need to check the rules not from top to bottom, but from bottom to top, from output to input, to show that if the outputs are true in an interpretation, so is the input. So for a conjunction, If a conjunction has both A and B true in some interpretation, then so indeed is the input A and B. So this conjunction rule works. We can go from simpler to more complex. For a negated conjunction, we're either working from the left branch or the right branch. If we're working from the left branch and I have an interpretation that makes not A true, then A is false, and that means that A and B is false, so indeed its negation not A and B is true. Similarly, if I was working from the right branch, if not B is true, that means that B is false, and so A and B is false, so its negation A and B is true. So whether we're working from the left or working from the right, we can go from output back to input. Either of the outputs is enough to guarantee the input. So I'll quickly work through the other examples to check that they work. If I'm in the left branch here for a disjunction, if A is true, then indeed A or B has to be true in that interpretation. Remember, disjunction is inclusive. Similarly, if I'm in the right branch, if B is true, then A or B is true. On the other hand, if A and B are false, if their negations not A and not B are true, then indeed the disjunction A or B is also false. For the conditional, if I've got A true and B false, because A and not B are both true, then indeed A implies B is false, so its negation is true. On the other hand, in the true conditional case, if A is false, that's enough to make that A implies B is true, or if B is true, that's enough to make A implies B true. For the biconditional, if I'm in the left branch here, that means that A and B are both true, which is one way for the biconditional to be true, and similarly, if A and B are both false, that's one way for the biconditional to be true. And finally, for the binary rules, if A and B have different truth values, one way for that to happen is for A to be true and B to be false, in which case the biconditional is false, or if A is false and B is true, that's one way for the biconditional to be false. Last rule is the double negation rule, and indeed, if A is true, then its double negation, not A, has to be true. So having checked all of the rules, we've shown that each of the rules works. If the output is true, either branch, it doesn't matter which, then so is the input. So this is enough to justify the completeness theorem. If a tree for a set of formulas stays open, the atoms and negated atoms on an open branch in the tree suffice to give us an interpretation in which every formula in that branch is true. The set of formulas is satisfiable. So what we've shown is that proof trees and truth tables give us the same result. We've shown that the boundary between valid and invalid arguments can be drawn in two different ways. So we've learned not only how to do logic, we've also learned a little bit in this case about how these techniques work. That's the end of the core section about basic logical techniques. In the rest of the lessons, we'll look at the connections between logic and other disciplines: computer science, electronic engineering, linguistics, and philosophy. Your aim should be to cover at least two of these topics. Now, since different people will want to choose different topics, we're going to release each of these topics at the same time. Jen will cover computer science and electronic engineering, and I'll cover linguistics and philosophy. Take them in any order you like, and choose as many as you like. 2 topics should be enough to get an excellent score in this subject, but the more you take, the more you'll learn about logic and how it's applied. So I hope you've enjoyed this section on the core topics of propositional logic, and we look forward to joining you in the next sections of our subject.